In this lecture, we are going to discuss about another topic related to image compression is interpixel redundancy. It is also called spatial and temporal redundancy because the pixel of the most 2D intensities arrays are correlated spatially. That is, each pixel is similar to or dependent on the neighbor pixel. So information is replicated unnecessarily. This type of redundancy is related with the interpixel correlations within an image. In video sequence, temporally correlated pixels also duplicate information. The code used to represent the gray level of each image have nothing to do with the correlation between the pixels. Because of the interpixel correlation within the image, the value of any given pixel can be reasonably predicted. Because of the interpixel correlation within the image, the value of any given pixel can be reasonably predicted from the value of its neighbor pixel. The information carried by individual pixel is relatively small. So much of the visual contribution of a single pixel to an image is redundant. So for example, the difference between the adjacent pixel can be used to represent an image. So transformation of this type are referred to as mapping. They are called reversible mapping if the original image elements can be reconstructed from the transformed data set. So interpixel redundancy implies that the pixel values are correlated. That is, a pixel value can be reasonably predicted by its neighbors. So as you can see, there are two figures, figure A and figure B, and that is a corresponding histogram of figure A and figure B. So histogram of both the images are similar. So now we find out autocorrelation. So as we have already learned about the correlation, so you know this formula. So we find out the autocorrelation along a line profile of this image and a line profile along this image. So you can see in this figure that at this position or this pixel at 45 or at 90, they are highly correlated. So we can see that this image is a highly correlated as compared to this one. So we can try to find out the correlation in the image to remove the interpixel redundancy. Now, to reduce the interpixel redundancy, the data must be transformed into another format. So there are various kind of transformation exists. For example, thresholding, discrete Fourier transform, discrete wavelet transform, etc. So I'm going to explain this interpixel redundancy with a simple example, that is a thresholding operation. So the size of the original image is 1024 cross 343, and that one is corresponded thresholded image, in which we are going to take that if the intensity value is greater than certain intensity value or t, then it will become 1. If it is less than or equal to t, then it will become 0. So this one becomes a binary image or thresholded image. So now if we plot a line profile along this one, we can find this way, this line profile, that the pixel on the x-axis are 1024 and this is corresponding intensity value. So as you can see that from 0 to 62, they have the same intensity value. So now we can represent this intensity value in this threshold image by 1, and up to which value? Up to 63 pixels. 0 to 62 means 63 pixels. So we are writing a run length encoding, that is 1 is the intensity value and 63 is the number of pixels up to which the intensity value is 1. So we need a 10 bit for 1024 and 1 bit for this one, is total 11 bit. Now again if we move here from here, to here. So up to 149 from 62 onwards or 63 to 149, the intensity value in the thresholded image is 0. So 0, comma 87, the difference between 63 to 149. Now from 149 to up to 195 means 37 pixel, the intensity value is again 1. Now from here we will find that for 5 pixel the intensity value is 0. For 4 pixel again the intensity value rises and it becomes 1. This is the threshold value, that is nearly 130, and after that this complete intensity value is 0. So next 556 pixels the intensity value is 0. Again for the next 62 pixels the intensity value is 1, and for the rest 210 pixels the intensity value is 0. So total there is a 8 pairs corresponding to this 1024 pixel. There is an 8 pair, and for every pair we need a 11 bit. So total 88 bits are required as compared to 1024. Now as you know that the original size of the image is 1024 cross 343. So if we perform the same operation for the entire image will be reduced to 12,166 runs. So now coding redundancy CR is equal to N1 by N2. So 1024 into 343 and corresponding 1 pixel, 1 bit, 1 bit, and this one is 12,166 into 11. So that CR comes out to be 2.63. So if we calculate the RD, then its value comes out to be 0.62. That is 62% of the data is redundant. So in that way, we can reduce the interpixel redundancy. So in the next lecture, we are going to study about psychovisual redundancy.